as a summary, we have discussed last time that carboxylic acids contain the carboxyl functional group, which essentially consists of the carbonyl group here and hydroxyl group here. Okay, and if you combine the carboxyl group with the alcohol, such as methyl alcohol, they can form what's called an ester. So a lot of different esters give various fruits the smell and to some extent the taste. So here are some examples. For instance, if you will combine pentanol, the alcohol, and butanoic acid, you're going to get the smell of apricots. If you combine butanoic acid and ethanol, the regular drinking alcohol, pineapples. And different combinations will give you different smells. For instance, propyl acetate will smell like pears, and pentyl acetate will smell like bananas. Okay? It's important to understand, and that's going to be crucial for our further conversations about biological molecules, is that esters, compounds that are formed by carboxylic acids and alcohols, can be hydrolyzed with acid. Okay? In this process of acid hydrolysis, water molecule supplies the hydroxyl group. So essentially what is happening here is that hydroxyl group attacks the carbon, okay, which results in the replacement of this OCH3 part with a hydroxide, and OCH3 plus hydrogen form methanol. So essentially, acid hydrolysis of esters brings you back to individual molecules of the carboxylic acid and alcohol. Does that make sense to everybody? So, I want you to understand that there is a substantial difference between the hydrolysis of esters that are done by acid versus by base. So when you mix your esters with acid, give it some heat, okay, and you're going to end up with carboxylic acid and an alcohol. When you do the same reaction but you use base instead of an acid, we call this saponification, because what you end up with is basically the soap. Okay? So in this situation, sodium hydroxide replaces the alcohol residue in the ester, but almost immediately forms a salt with the sodium. So for instance, if you take methyl acetate, treat it with sodium hydroxide, and heat it up, you're going to end up with a salt, sodium acetate, and methyl alcohol. Does that make sense to you folks? Now, this reaction will become, like, we're going to go back to it when we're going to talk about lipids because saponification implies that we're producing soap. And a soap, by and large, can be produced by treating lipids with various bases. Making sense so far? We're probably going to go back to it today. So far we discussed carboxylic acids. We discussed esters. Now let's talk about amines. So it's a little bit of a, new concept here. Amines are derivatives of the ammonia molecule. In amines, one or more hydrogens are replaced with organic substituents, alkyl substituents, or aromatic substituents. For instance, this amine has 3 substituents. It has 2 methyl groups and 1 propyl group. Okay? Dimethyl propyl amine. This one has only 2 substituents, ethyl and methyl. So ethyl methyl amine. Okay? Now this compound is quite famous. It's called aniline. Okay, or benzylamine. Why I pay so much attention to aniline? It is a dye. It can stain clothing, for example. It can stain fabric blue. And humans discovered that amines, at least a lot of them, especially aromatic amines, can work as dyes when they first isolated indigo, which was the go-to blue dye before the advances in synthetic organic chemistry. Now, amines are classified in a way similar to alcohols. Do you remember primary, secondary, and tertiary alcohols? We're talking about them. Remember those? Amines are classified based on the same principle. So, this is the molecule of ammonia. If you replace 1 hydrogen on ammonia with some kind of the organic substituents, okay, you're going to get primary amine. Just 1 hydrogen is replaced. Am I making sense? If you replace 2 hydrogens, you can get a secondary amine. And if you replace all 3 hydrogens, you get tertiary amine. So you absolutely should be able to distinguish between those. Making sense, everyone? All good? So, some amines can be aromatic, which means there's a benzene ring involved. So this is aniline. The aromatic amine that I mentioned before is a dye, right? Now, here's the thing. If you look at this particular molecule, there are 2 kinds of hydrogens. Now, pay close attention to what I'm about to say. There are 2 hydrogens that are connected to a nitrogen atom. Do you agree with me? And then there are 5 more hydrogens, we just don't show them on the formula, which are connected to these 5 carbons. Do you agree with me? So, at the end of the day, when you put some kind of a substituent, some kind of a replacement instead of a hydrogen, you have to specify whether this replacement goes connected to another carbon or it replaces one of these nitrogen bonded hydrogens. Am I making sense? So for example, the molecule in the center for bromoaniline, it means that bromine replaces a hydrogen located at a carbon. On the other hand, in N-methylaniline on the right, you have a methyl group that replaces one of the hydrogens connected to nitrogen. For situations like this, we use the prefix N. If alkyl group replaces the hydrogen on the nitrogen atom, we're not just calling that methylaniline, we call it N-methylaniline. Does that make sense to you? Line angle formulas, I'm not sure what to enlighten you about, but you familiar with them? So here you have primary propyl amine, because there are 3 carbons, therefore propyl. Here you have ethyl, propyl, 3 carbons, amine, and since 2 hydrogens are replaced, it is a secondary amine. And here you have a tertiary amine, diethyl, so 2 ethyls, and methyl amine. Now remember, when you select the order of substituents in the name of the organic compound, you have to use an alphabetical order. So methyl comes after ethyl. Does that make sense? So go diethyl methyl amine. Now, virtually all the amines act as bases when they are dissolved in water. Okay? Particularly primary and secondary amines. We're going to talk about the tertiary for a little bit. So what essentially happens, remember the Bronsted-Lowry theory of acids and bases? According to Bronsted and Lowry, a base is something that can accept hydrogens. Does that make sense? Something that can accept hydrogen cation. So nitrogen atom in both ammonia and the primary amine, for example, they carry a lone pair of electrons. So if they encounter an extra hydrogen ion, they can quote-unquote neutralize that positive charge on a hydrogen ion by the means of the lone pair. So what you end up with, if you use ammonia, you end up with the ammonium ion, a typical, so ammonia serves as the Bronsted-Lowry base. But if you will dissolve methylamine in water, it will also act as Bronsted-Lowry base, accepting the hydrogen and forming methyl ammonium ion. Does that make sense to you? Everybody? Good? Okay. So, since amines act as bases, even though they are Bronsted-Lowry bases, they're still bases. The base can be neutralized by the acid. Does that make sense to you? So, Fishy order is due to a certain set of amines and other heterocyclic compounds that contain nitrogen. Okay? And since amines are bases, they can be neutralized by an acid such as citric acid. When you cook fish and you want to get rid of that fishy smell, you basically squeeze some lemon juice into the fish and let it sit for a while, and citric acid from the lemon juice will neutralize those bases and will make fish smell less fishy. Okay? So in this example, you see not citric acid but hydrochloric acid, but essentially the reaction remains the same. So you have an amine, primary or secondary, which in this particular case interacts with the hydrochloric acid, resulting in the amine salt. So you go from amine to ammonium, and you put the alkyl substituent in front of the name. So methyl amine becomes methyl ammonium chloride. Dimethylamine becomes dimethyl ammonium chloride. So far, so good? So a lot of amines are important biological mediators, okay? And the main point is these amines are very inconvenient to work with when they are in the amine form. They're usually gases or liquids with a really low boiling point. It's inconvenient. But if you convert it into the ammonium salt, you end up having a solid compound that is soluble in polar solvents such as water, which comprises most of our bodily fluids. Does that make sense so far? A lot of amines are used as drugs. So this one on the left, ephedrine, you can see there is a primary amine which forms a salt with a hydrochloric acid. Okay? Does that make sense? So ephedrine is a nasal decongestant. This guy, diphenhydramine, is a quite potent anti-allergy medicine. This is actually one of my favorite ones because in the form of a cream, diphenhydramine can relieve itching because of the mosquito bites, something like that, okay? In the liquid form, Benadryl can relieve the symptoms of allergy. My favorite use for this, though, and I'm quoting our kid's pediatrician back in the days, when we asked him how to make him sleep through the flight, he went, I just give him some Benadryl. Benadryl is, in addition to its anti-allergic properties, also a very potent, basically sleep medication. Okay, it's not going to treat some severe insomnia, but it really makes people drowsy. Sounds good? Okay, let's move on. So another example of the ammonium salt is cocaine. Okay, so here you can see on the left cocaine hydrochloride. Okay, that makes sense? Now this is the salt. If you treat it with sodium hydroxide, you can precipitate it, and this is how crack cocaine, which is a smokable one, is pretty used. Not that I'm particularly aware of the usage modalities, you know. Another important category of amines, so-called alkaloids. So I'm going to muse a little bit about all linguistics that are contained within that word. Alkaloid is an Arabic word. Al-Kali, okay? So it's an Arabic word. What do you think Al-Kali means in Arabic? You absolutely know what it means. 100%. So again, when something is alkaline, what does that mean? It's a base. That's it. Yep. The word alkali in Arabic refers to a base. It was discovered like centuries ago by Arabian chemists. And basically, the huge category of compounds that are isolated from plants, called alkaloids, they all share the same feature. They have this very basic nitrogen atoms. Okay? One example of alkaloids is nicotine. Okay? Sounds fair? But it's not the only one. Do you like coffee? Do you? No? Okay, fine. Well, anyone except me? Yes? Caffeine is an alkaloid. Tea? Yes? Theophylline, the main stimulant in tea, is an alkaloid. Chocolate. Theobromine is the main stimulant in chocolate. A lot of alkaloids are biologically active, and many of them actually are quite poisonous, like nicotine. In large doses, it can kill you. Okay? Does that make sense? Now, well, yes, nicotine does activate pleasure centers in the brain, but I can tell you this, and I'm fine with it. I smoked for 22 years. Okay? I loved every second of it. Because nicotine acts on the same receptors as one of the neurotransmitters in your brain, acetylcholine, does. So when people, if you know someone who smokes, ask them how they feel after they have a cigarette. People will often say that they have a clearer mind, they cognitively better. True. It is absolutely true. Nicotine by itself is a pretty powerful nerve stimulant, which can increase your performance temporarily, obviously, that kind of stuff. Does that make sense? So what I'm trying to tell you is that nicotine itself, it's a neurotransmitter, basically. It's a stimulant. If you overdo it, yeah, it's going to be a problem. But it's a drug, just like any other drug is. In large doses, it can kill you or form an addiction. But in the small doses, it's just a drug. I'm not encouraging anyone to start smoking. Okay? That makes sense? So, something that I mentioned, so coffee, tea, chocolate, they all contain caffeine, but to be fair, the greatest concentration of caffeine is in coffee, tea is going to be theophylline, and chocolate is going to be theobromine. Another alkaloid here, you can see the tertiary amine, morphine, okay, codeine, and all other derivatives of it. Does that make sense? So basically what we call opioid drugs is another example of a pharmacological compound that can be misused. Am I making sense? Morphine or codeine by itself, pretty potent painkillers. Okay? So is heroin, so is OxyContin, so is fentanyl. However, because of the mechanism of action, they all can lead to addiction. Does that make sense? I'm not defending the drug addiction. What I'm trying to tell you is that all these are drugs. You can perceive them as illegal drugs that make people high, or you can perceive them as pharmacological compounds that relieve the pain. Am I making sense? Fentanyl is actually much better than any other opioid because it is extremely potent. From a pharmacological point of view, it's fantastic because you need just a tiny little dose to get to a therapeutic effect. Unfortunately, because it's so potent, it has much greater potential to lead to addiction and overdose. Does that make sense to you? Okay.
So those opioids, they don't give any name. How can you know which ones?
Okay, now what we were talking about were amides. Now we're going to talk about amides. Okay, that. So an amide is the structure similar to an ester, but when ester is formed between carboxylic acid and an alcohol, an amide is formed by carboxylic acid and an amide. So, this is an example. Look at this. So you have a carboxylic acid, okay? Acetic acid, vinegar. So you replace the OH group in the carboxylic acid with the nitrogen and relevant hydrogens. Okay, so this is the simplest amide, acetamide. So far, everybody follows me on that? You replace OH with NH2. Now, does it have to be NH2? As you can see from an example with acetaminophen, no, it doesn't. So for instance, let me give you an example of a slightly different amide. So let's say we have acetic acid, right? Make sense? An example that you see on the slide, OH group is replaced with NH2. Making sense? What if instead of NH3, instead of ammonia, you're going to use this? So you can replace OH group and generate an amide that would have the following structural formula. Does that make sense? Okay? Good. If you wonder about the name, first of all, this is acetamide. And here you have a methyl group connected to a nitrogen, so it's going to be N-methylacetamide. Does that make sense to you? Now, if you think about the byproducts of this reaction, you have to ask yourself, this blue part, like this compound, what gets into an amide? An H and CH3, so we have a hydrogen left behind. And when OH group is replaced, OH group and the hydrogen together will give you water. So it's a byproduct of that synthesis reaction. Okay? Reasonable? So, one of the most famous amides is urea. Urea is essentially the product of the breakdown of proteins, and due to this NH2 groups, urea is very basic. Does that make sense? So when your cells break down proteins, they produce urea. If urea is not filtered out of your blood, it's going to make your blood to become more and more basic. Making sense? Which can lead to a variety of conditions, from seizures to general, organ shutdown. Does it make sense to you all? I'm going to tell you something. Does anyone use chewing gum? Yeah, the chewing gum. Sugar-free, please. I mean, what kind? Yeah, it's probably sugar-free. Yeah. Well, if you use chewing gum, you can look at the ingredients of it. And there can be one ingredient there called carbamide. Especially if we're talking this, like healthy teeth kind of stuff. I don't remember the names, but there are like, the gum that you're supposed to like chew after you had a meal. You know what I'm talking about? To kind of restore oral pH. I mean, I honestly, I don't use it so much. But if you look at the composition of some of the chewing gums, you're going to find a component in them that's called carbamide. It's urea. Urea by itself is fine. It's just a base. Does that make sense? Okay? I'm going to give you a little bit more context here.
So why do they use that?
Because it's base. When you eat something, your mouth becomes acidic, and it's not good for enamel on the teeth. So when you add some carbamide, it neutralizes the acid. Am I making sense?
When you swallow it,
Well, urea itself isn't bad or good. It's just a base. And the amounts are so low in the gum that all it is good for is to neutralize the acid that's formed in your mouth after the meal. Am I making sense? So, another thing about urea that I wanted to, kind of highlight. We're going to get pretty physiological here. Did anyone ever smell fresh urine? How does fresh urine smell? No. Fresh urine doesn't smell strong. Fresh urine there's almost no smell to it. I'm not talking about people with ketosis, diabetes, that kind of stuff. Like a healthy person pees, it doesn't smell. Well, you probably can tell if, there's a spot on the street that people peed a lot on, right? So what smells then? Turns out that this chemical, urea, can be digested by bacteria that are normally present in your skin and inevitably end up in the urine. Does that make sense? When they digest urea, they produce ammonia, and what you actually smell when we say, oh, it smells like pee, we smell ammonia that is derived from urea. Does that make sense? Now you can see that a lot of nitrogen-containing chemicals serve as drugs. We've already mentioned painkillers, such as opioids. We mentioned amides, such as acetaminophen. Okay? This is another example of an important amide. Okay? Phenobarbital and pentobarbital. Okay? So they are sedatives, okay, and sleep inducers, but in the common tongue, do you know, like in the criminal area, what these drugs are known for? What is the name for those drugs? Phenobarbital and pentobarbital. This is some of the rape drugs. These are the drugs that used by criminals to induce sleep. Okay? They lack the taste. So, okay, so that wraps up our conversation about carboxylic acids. I want to remind you all that this is the end of the material that will be on the next exam number 3. Lipids aren't there. Making sense? Okay.